Okay, so this is the next lecture in my series on algebraic number theory. Today we're going to talk about discriminants, but hopefully we're going to relate it more to the application we have in mind, number fields. So the overview of this section. There are two main results that I want to get to. The first is it's kind of like a like a strengthening of the last result that we proved in the previous section. So this is going to be a result relating discriminants to number field or submodules. Sorry. And the second condition is going to be the second half of this lecture is going to be about using our Galois theoretic formula for a trace to get a Galois theoretic formula for the discriminant. Okay. These are the two main things. So let me go ahead and tell you what this discriminant in submodules thing says. So this is going to be 21.1 proposition. Okay. So for the most part, all our applications are going to be when A equals Z. So we're going to let A be the ring Z. And let's say B a finitely generated, or I guess, okay, B a ring extension of A, which is free and finitely generated. Finitely generated over A as an A module. Okay, so this is the setting in which it makes sense to talk about discriminants. I guess A doesn't have to be Z, but B has to have these conditions to ring extension, which is free and finitely generated. Okay, we're gonna let's say gamma 1, gamma m, b and b, and let's say n is the submodule generated by these guys. So A gamma 1, gamma m, the submodule. So this is different than the subalgebra. Submodule generated. So basically a linear combinations of the gamma sub i's. Submodule generated by the collection of gamma i's. Okay. Then basically we have two conditions. One. Then the discriminant is non-zero, so the discriminant of these guys is not equal to 0 if and only if n has finite index in B. Okay, and 2, if n is a finite index then the discriminant of these guys. Oh, I think there maybe should be an additional hypothesis. They should be assuming that the discriminant of B over A is non-zero. Okay. So I need there needs to be some like non-degeneracy condition on the trace form. If n is a finite index, then we have this relation. Not determinant, sorry. Okay. This needs to be non-zero. This needs to be the index NMB squared times the discriminant of the extension. Okay. So there are really two things we need to prove here. And the key is basically the following. Recall from lecture 20 that we have the following formula for the discriminant of the gamma spies. Discriminant of these guys is equal to the determinant of the change of basis matrix. So if gamma sub I equals alpha ij beta sub j for a basis beta sub j equals 1 to n, and then this guy is going to be the determinant of these alpha ij's, that determinant squared, times the discriminant of these beta sub j's, which is the discriminant of the extension. Here we're using z in that, so maybe an aside. We use that since a equals z, the discriminant is a well-defined integer. Okay, so essentially what the claim is that so the claim reduces to the following. Okay, so 1 reduces basically to this determinant is 0 if and only if this index is infinite. So alpha ij equals 0 if and only if the index of b and n equals infinity. So this is equivalent to 1 up here using this formula. And 2, if this guy is a finite index, then the determinant of this guy is actually equal to the index on the nose. Okay, so how do we see 1 and 2? Well, first let's focus on 1. Well, basically the idea is we have the following sequence of equivalences. The determinant of this guy is equal to 0. if and only if this matrix is not invertible, or sorry, no, that's not quite right. What does it mean for the determinant to be 0? It means that the columns are linearly dependent. Okay. If and only if the columns are linearly dependent. And here we can assume that this linear dependence happens over Z. I guess normally it would happen over Q, but if you clear denominators, you'll get one that happens over Z. So clear denominators. Okay. Okay, so what does it mean? What happens when the columns are linearly dependent? I want to say this. Essentially what happens is the rank of the matrix doesn't have full rank. So maybe there's a better way to do this. I see. Okay. So the columns are linearly dependent over Z. I think the condition that I'm missing here is that these should have the same number of elements. So really this should be free and finitely generated of rank M. Okay. If M is smaller, basically, then this discriminant is just always going to be 0, because this matrix will let's see. Oh, it doesn't make sense to take the determinant of a not square matrix, I guess. So really, yeah. So this is the thing that was confusing me. This M should be the same as this M. Okay. Okay. So once I know the columns are linearly dependent, then I know essentially that I guess okay, so what does this tell me? Maybe I'll go about doing this a different way, I think, now that I've thought about it a bit more. So I think so let's go ahead and focus on 1. So let's just think what happens if the determinant of these guys is 0. Okay. Well, and essentially we can find some linear, non-trivial can find some non-trivial linear relation amongst these gamma sub i's. Okay. These things aren't actually a basis for n. I want to claim that n can be generated by a smaller number of generators. Claim n can be generated by a smaller number of generators. I guess, so since n is contained in B and B is free, right, I can find a basis for n. N is free, and hence I can find a basis. Okay, let's call this basis eta 1 through eta L. Okay, and I know that I see. So I know I can write so since these things are in n, I can write eta I is equal to some, let's say, Cij gamma j, and since these things are a basis for n, I can write gamma I equals sum over dij eta sub I. Okay, so from these I get a couple matrices. Matrices C, D, how do I show that L has to be less than M? I see. If L equals M, then I can essentially, then the linear combination of gamma i's that is 0 will induce some linear combination of eta i's which is 0. So that's the idea. So the linear combination of gamma i's, which is 0, will induce. Okay, so forget the matrices. Will induce a linear combo of eta i's, which is 0. So I know, so I've got some linear operator. I have a linear operator, a z-linear operator, let's say t from n to n, which sends, let's say, eta I maps to gamma I. So assuming they're, L equals m, then I can define this linear operator. Then I can find sum of ci gamma I equals 0, which implies that this sum of t, basically that t of the following sum will be 0. T of the sum of ci eta I equals 0. Okay. And then I need essentially I need an inverse to t. So the question is now, can I find L let's say sending gamma I to eta I. And I think the answer is yes. So I need to use basically this matrix of Cij's here. So how do I know that I can do this? Consider if, so let's say if eta I equals the sum of the Cij's gamma j, consider how does this matrix actually act on n? Okay, so every element of n yeah, maybe this matrix C doesn't actually go quite the way I'm expecting. I guess what does this tell me? This tells me that T has non-trivial null space. Okay, maybe there's a different way. So T, alright, I can see that T is surjective and that T has a kernel. So maybe forget this. We see what do we see? We see that T from n to n is surjective since the collection of CIs is not all zero. Then this sum Ci eta I is not equal to 0, and hence the kernel of T, right, is non-zero. Okay. So what do we see? By the first isomorphism theorem, n is isomorphic to n mod the kernel of T. Now this is definitely a contradiction. How do I want to say this? This is a contradiction. Why is this a contradiction? I think the easiest way to see this is by the what you call it? Basically by the structure theorem for finitely generated, or for, yeah, this is a contradiction by the structure theorem for free modules. For free. Essentially, kernel of T has to also be a free module. And I take a free module modulo a free module, this thing's going to have a smaller rank than n. So let me explain this a little bit better. Since ker T is a submodule of n, ker T is free. Thus, the rank of n is strictly less than the rank. So yeah, there is a little, you should probably be more careful than this, but this is the basic idea of what's going on here. Okay, so L is less than M. So what do we show? Thus, L is less than M, and N, basically the index of N and B has to be infinite because since the rank of N is strictly less than the rank of B. Okay. Okay. So this is basically one direction of number one. So let's suppose this index were infinity. Then what happens? Then the rank of N has to be smaller than the rank of B. Thus, these gamma i's are not a basis. And they have a non-trivial, they satisfy some non-trivial linear relation. They satisfy some non-trivial linear relation which causes the determinant to be 0 of our matrix alpha ij. Okay, so there's one. Two is a bit easier. Basically, we've more or less already proved this. Two immediately follows. This immediately follows from our lecture 16 notes from proposition 16.5. Notes on free modules. Okay, so I'm not going to say anything more about 2. Okay, so this proof turned out to be harder than I remember it being, in particular condition 1 here. But the basic idea is that this index, this determinant being 0 forces this N to have smaller rank than B, which in turn forces this index to be infinite. Okay, so let's go ahead and move on to focusing on the discriminant and its relation to Galois theory. Okay, so essentially what we're going to do is we're going to write down a formula for the discriminant, but we're going to use this previous proposition about our formula for the trace in terms of Galois theory. So this will be 21.2, sorry. And this will be another proposition. Okay, we're going to let L be a finite separable extension of a field K. And let's say this extension has degree m. k. So we're going to let omega, let's say, be a Galois extension of L. And we're going to enumerate our k embeddings. Distinct k embeddings. So this should remind you of our notes. I want to say it's lecture 17 on trace, norm, and Galois theory. K embeddings of L into omega. Okay, and the claim is as follows. Then for every basis, beta 1 through beta m of L over K, we have the following formula. The discriminant of beta 1 through beta m is the determinant of the sigma sub I beta sub j, this determinant squared, which in turn is not equal to 0. So this formula is useful, but the really important thing is that this is non-zero. So this is going to tell us basically that our trace form on finite separable extensions is non-degenerate. So this is going to end up being very useful in the proof that rings of integers are finitely generated C modules. So first, we basically need to recall the following. First, recall that the trace over K of beta, this is the sum of sigma I of beta. So this is trace, norm, Galois theory, lecture 17. So essentially the trace is the sum of the Galois conjugates of an element beta for any beta in L. Okay. And then we have, basically by definition, the trace. So the ij entry of our matrix. Sorry, what am I saying here? Grab my eraser. So what? Okay. The discriminant of these guys, beta 1 through beta m. Well, this is the determinant of the trace of the product. Okay. So this is the Gram matrix with respect to the betas. Okay, and remember our bilinear pairing here is the trace, which you multiply the two elements and then you take their trace. Okay, and note that the trace of a product J is the sum, since these things are algebra homomorphisms, they'll split over the product, each k embedding of L into omega will split over the product. Okay. And then if you just think about the matrix multiplication, this is the, what do I want to say here? Note then that something like maybe trace of BM, which is, I'm just changing the variables here so that it makes it easier for me to think about. Beta L, sigma sub I beta L, sigma sub I of beta M is the Lmth entry of the following matrix of basically the product of what do I want to say here? The Lm entry of the product of the following two matrices of A equals sigma sub j beta sub I and B equals A transpose, which is sigma sub I beta sub j. Okay. If you just perform the matrix multiplication, then you'll find that this is the case, and the discriminant of these guys is the determinant of A times A transpose, which is the determinant of A squared, which is exactly the thing that we want it to be. So the determinant of sigma I beta j squared. Okay, the last condition, so why, so question, why is this non-zero? The short answer is basically Dirichlet's theorem on what you call it? The short answer is basically, I want to say Dirichlet's theorem on linear independence of characters. So if some ci, so it suffices to show the columns are linearly independent. So it suffices to show the columns is matrix B sigma 1 beta j sigma m beta j are linearly independent. Maybe the I and the j should be swapped, but it doesn't matter. Basically, if there's some linear combination which equals 0, let's add some ci sigma 1 beta j sigma m beta j. Say this, I knew this was equal to 0. Then, okay. Yeah, I guess there are a couple different ways to view this. So then sigma 1 of these Okay, I see. And this equals 0. And this is a sum over these should match. I see, okay. Should be a sigma c sub j, and the beta sub j should match because this should be a sum over j. Okay, so this should be j, this should be j, okay. And this should be sigma sub I, this guy is equal to 0 for all I, between 1 and m. Okay, so essentially I've got some linear combination of my basis, which is in the kernel of all these sigma sub i's. Let's see here. Oh, basically what I want to say is if all my Galois conjugates are 0, then that element has to be 0. So since all the Galois conjugates of this guy, Cj beta sub j, are 0, and this thing is also 0. Cj beta sub j equals 0. But these guys are a basis. Are a basis. So I guess in here there's some field theory going on. And if you're questionable of this claim, I would look in Milne's notes. These beta sub j's are a basis, and hence the c sub j equals 0 for every j. And thus the columns are linearly independent. Thus the determinant of this matrix A is not equal to 0. Okay. Yeah, essentially, yeah, it's a bit odd. So there's something slightly confusing, something that makes me think something is wrong, because really I could just use the fact that these things are embeddings. And then, but then I only would have had to have one here. But I think it's fine. So I'm just gonna ignore that issue for now, and maybe I'll make a correction if I figure out something's wrong. Okay, so this is the important part is basically that you can compute the discriminant by using the determinant of these Galois conjugate matrices, and it's non-zero, so this discriminant is a non-degenerate bilinear pairing on L.